I'd like to prove to you why, if a function is differentiable at point A, then it is also continuous at point A. So we begin with having a function f, and we say that f is differentiable at x is equal to a. This implies that f is also continuous at x equals to a. So the statement basically is saying differentiability implies continuity. Now the converse is not true. I cannot say continuity implies differentiability because one example is the absolute value function, where even though it is continuous everywhere, okay, it is not differentiable at this point x equals to 0, y equals to 0, 0 comma 0, because if you use the definition of the derivative and you let x approach 0 from the left versus the right, you will get two values. One is -1, the other one is 1. So since the two-sided limits don't equal each other, then it is not differentiable at this point. Okay? And actually, visually speaking, if you take some sort of like a straight edge and you try to pivot around this sharp edge, really, what does your tangent line look like, right? There's actually like infinite amount of possibilities that you could handle your slope, okay? The slope of the tangent line. So without further ado, if we start with the statement that f is differentiable, right? We know that f is differentiable at x equals to a, okay? So let's say we want to start with the limit as x approaches a of f of x minus f of a, right? I'll just start with this limit expression, okay? I currently cannot say that the limit as x approaches a of f of x is equal to f of a. I'm trying to show that, right? I'm trying to show that f is continuous at a, okay? So I can only leave it like this for now. But what I could do is that I could multiply and divide by x minus a. Now why is that helpful? It's because I said in my premise, in the antecedent, that f is differentiable at a. What that means is that in this part over here, this limit definition, or actually I could split this up using limit laws. So the limit of the product is the product of the limits. So we have limit as x approaches a, f of x minus f of a, over x minus a, and we can multiply it by the limit as x approaches a of the expression x minus a. So this is actually one of the limit definitions for derivatives. So this calculates the derivative of f at a. And we know that it is differentiable at a, so we can call this f prime of a. Okay, so this is the derivative of f at a, and we denote it as f prime of a. Okay, f prime is the derivative function of f, and I could evaluate it at x equals to a because I know that the derivative exists at x equals to a. So we have f prime of a. That takes care of this first limit expression. What about this part? Well, I'll just write it out again. So it's the limit as x approaches a of x minus a. Okay. Oh, and by the way, since f prime of a exists, we know it's just some real number. Okay, it's just a number. But to evaluate this limit as x approaches a of just x minus a, well, this you can just plug a into x since this is a polynomial. Okay, and of course you could use the limit definition and go through all the steps, and you will realize that yeah, you could yeah, you could do it like that using epsilon delta or anything, something like that. But we won't be doing that here. So we have a. You plug it into here. Okay. So we have this is just equal to f prime of a. And then plugging a into x, we have a subtract a. What is the number subtract by itself? Well, a minus a is just going to be 0, right? So we have this is equal to f prime of a multiplied by 0, okay? Which equals to ultimately 0. Okay. Why is this helpful? Because initially, I should actually write this again. So initially, I wrote down limit as x approaches a of f of x minus f of a, okay? And then what I did right here was I multiplied top and bottom by x minus a. But this was my original expression over here. And I found out towards the end that it equals to 0 based on this premise over here. So what does this mean? This means that I could move this f of a to the other side because I actually concluded that this limit over here is equal to 0. And of course, I could use limit laws and say that the limit of the difference is the difference of the limits. And if you take the limit of a constant, because f of a is just a constant, the limit of a constant is just the same constant. So I won't do that. But you add f of a on both sides, and you get the limit as x approaches a of f of x, and this is equal to f of a, which is precisely the definition of continuity of f at the point x equals to a. This is what we actually want to show, that the function f is continuous at a. So if it can follow this formula right over here, then we know that we are good to go. So that completes the proof.